Alright, so this is just a quick run through of some examples performing linear regression using scikit-learn. First I'll just go through a basic linear regression, and then we'll go deeper with a test-train split and a train-test split, and add some polynomial features, and do our own kind of cross-validation to see what degree polynomial is the right degree to use to predict new values. So first we're going to look at the Sacramento housing data set, and we're going to use Pandas Profiling to give us a little report on the data. And here it's telling us that latitude and longitude are highly skewed. There's some zeros in beds and baths, and it's throwing a warning on street because there's 981 different streets and 3 duplicate rows. So then we can look at the correlations. We see that there are some high correlations here off of the main diagonal. We'll deal with that a little bit more in our next data set. And we can make a scatter plot of the different houses, include the number of baths and the price as features in the plot. We see that now we have a data frame with 985 entries. I'm going to go ahead and drop the street, city, state, price, and sale date, and keep the rest of the variables as my input values, my x, and we're trying to predict the price. So that's why I dropped the price, because that's what I'm trying to predict here. And okay, so now I have the zip code, beds, baths, square foot, the type of residence, and the latitude and longitude. I'll go ahead and create a data frame that has the dummies, and I'm going to go ahead and drop the first, like we discussed. Again, we'll do a little more with with collinearity in the next example. And then I have this data frame that has my variables coded appropriately. And that's what I'll let now I'll call x this thing that has my encoded variables. And the normal procedure: instantiate a linear regression model, fit it, make some predictions, and see how we did with mean squared error and then root mean squared error. So in this example, our baseline was like almost $120,000. So that's not a very good model, because we're predicting house prices, and this is not a good amount of error. So we can also look at the coefficients if we want, and we see that these are all, a number of them are fairly big, and this could be a problem. We'll deal with this later, but just something interesting to consider for the moment is how large these different coefficients are of our model. If we wanted to, we could make a little function that goes through that procedure of instantiating the model, fitting it, making some predictions, and spitting out the error like we have here. So still we're at about 120,000. Okay, so that's just a basic example. We dropped a couple of variables. We coded our categorical variables, and then we fit a model. So in the next example, we'll use a little bit bigger data set, the California housing data set. And again, we'll look at the profile report. And this time, notice that it tells us that households and total bedrooms are highly correlated with population and total rooms. So I'm going to drop those pretty early on, just because of the problems with collinearity. And this is one of the nice things about using this profile report, is that it throws a flag on these right away. So, okay, there's no missing, and there's about not quite 21,000 rows. Only one of them is categorical, so we don't have to do too much encoding, and 7 others are numeric. So let's see here. Here's our categorical one, the ocean proximity. A couple different values here. Correlations, as you can see, there's very high ones between total bedrooms and rooms, like we were told. Okay, so I'm going to go ahead and I'll drop those households and total bedrooms, and then we can look at how many different kinds of houses we have in certain places. So we see that there are some classes that are really different. We'll talk about this at a later time, how we might want to approach dealing with these kind of categories that have such different proportions in a data set. But for now, if we look at this, we can see that the island is by far the smallest group. And also, if we do a little EDA and group it by those categories of ocean proximity and look at the mean of the median house values in those categories, we see that the island is by far also the most expensive, with a 380,000 mean median house value, followed by near the bay. So again, now I'm going to take this data, which I dropped those columns that the profiling told me we were highly correlated, and code the ocean proximity, and you see that then I have these four categories here. We dropped the first, less than 1 hour from ocean, and nothing that's super strongly correlated, so that's okay. And if we see the correlations for the median house value, we can see that here we have some that might make sense to just use as a starting place. So that's what I'm doing here, is I'm just selecting from those. Again, this is my data frame that has the dummy encodings, and I'm just selecting a bunch of these variables that have higher correlations with the median house value. And my y is going to be my median house value. And if we just take a quick look at this model, linear regression model, with nothing done to it, and the root mean square error, we have 73,000. So now let's go ahead and add some complexity. First, we're going to use the train and test split approach to building this model. We're also going to put some polynomial features in there to begin with. Remember that when we were using polynomial features, after we add the polynomial features, we're going to go ahead and perform a linear regression. So we combine those two with a make pipeline method here. And this is just a quadratic polynomial, so we just add a quadratic term to see how this does. And in this example, okay, we got a little bit better, 71,166. Now I can go ahead and I wrote a function that takes in an x, a y, and an n for a degree of a polynomial. We'll create a train and test split, make that pipeline based on that number, that degree, and spit back the performance of the model. What we can then do is we can loop through a few different values for n. So if we go ahead and write a little loop that rips through and applies those values for the different degrees, we can see how the RMSE is changing as we increase the degree. And you see here, notice here that it may be counterintuitive, but this higher degree is actually performing much worse than these earlier ones. This degree 6 has almost more than twice the RMSE of the degree 5. All right, The thing I didn't do in this function was provide a way to save those values and take a look at them. So I just add in um, a list here, an empty list for RMSE and degree, and pop those on as this function works. So same kind of results, and now I have a list of RMSE values. So let's go ahead and actually, what I do here is take and go 5 times for each degree, just so that we have a few different results to compare. Now this takes a minute, especially when you get to the 7th degree. So, but what this is doing is showing that we're getting a little bit different values each time, because we're working on a different train and test split each time through. This is just a random selection of train and test splits 5 times. It's kind of a naive cross-validation. So because we saved these degree values and the error values, we can create a data frame out of them and then look at some plots. So for example, if we look at a box plot for the distributions of those errors across the degrees, we see that they not only is the lowest error seem to be in the degree 3, but as you increase, the variance of that error is increasing as well. These boxes are much larger and wider as you increase the degree up here, and we see that root mean square error just growing and growing. And so if we want to look at the smallest, yeah, for sure, it's the degree 3, and that's at about 69,688. And again, if we take a look at where that is in a scatter plot, you can again see that as you increase the degree to 3, you're decreasing the root mean square error, but thereafter you're not only increasing the root mean square error, but we're increasing the variance of the root mean square error. So each time, we did it 5 times, but these guys are pretty tight together, pretty tight together, pretty tight together. That's an important thing to consider as well. So our best model, this guy, degree 3, and we're getting root mean square errors around not quite $70,000. So there it is.